Hello, please take your seats. Welcome back from the coffee break. And now I have the enormous pleasure of introducing Sara Hooker to you. Sara Hooker leads Cohere for AI, the dedicated research arm of Cohere. And with a long track record of impactful research at Google Brain, Sara brings a wealth of knowledge from across machine learning. Her work has focused on model efficiency training techniques and optimizing for models that fulfill multiple desired criteria: interpretable, efficient, fair, and robust. Sara leads a team of researchers and engineers working on making large language models more efficient, safe, and grounded. So please, a big applause for Sara.
Good afternoon, Khipu. Good afternoon. It is so lovely to be here, and I'm really looking forward to this talk. This is the last talk of today, so did we find the microphone for questions? We did. Where's the microphone? Okay, excellent. You are our first victim. Let's all stand up. I would like to play a short game to bond us all as a group as we go into this very serious topic. So please stretch your arms to the ceiling, to the side, to the other side. And now we're going to play a game. So it will work like this, and let's see if it works. The person who has a microphone will pass it, and as you pass it, say a language. There's only 2 rules. The language cannot be repeated. It has to be new. And we're all going to clap after each language. And we're going to see how far we can go. So let's keep it quick. Okay, so I will begin. So I will say English. Okay?
Portuguese.
Spanish. Alemán.
Korean.
Chino.
Italiano.
French.
Japanese.
Indonesian. Mandarin. Africans.
Hindi.
Mapudungun.
Swahili.
I think we
Russian.
No. You get one more go. Otherwise, we have to stop it here. A lot of pressure.
Arabic.
Ukrainian.
Finnish.
Quechua.
Danish.
Indonesian.
Oh, okay. We're done. Officially 2 strikes. Thank you, everyone. You may sit down. Amazing. Okay, this was a good way to begin. I will not be talking about our work on multilingual today, but we do also have a lot of work on multilingual, so I'm happy to chat separately. Feel free to find me. We did 101 languages, so maybe that exercise highlights the complexity of getting to 101. And in general, our lab does a lot of work on just how do we make AI work for the globe, and so I'm happy to talk about it. We also just work on multimodal. We released a vision model. And the other thing I just wanted to briefly mention in case it's interesting is that we give out a lot of research grants for compute. So if people are interested, I know a lot of people are studying, feel free to also ask or talk to me about it afterwards. But today's topic is something that I've just been thinking about for a long time. And I thought it's very timely to talk about. It's this question of whether our primary ingredient that has fueled a lot of our favorite recipes over the last decade will be our primary ingredient going forward. I'm going to talk about the diminishing returns to scaling. And I will ask you a question today, which is at the heart of our field, which is bigger better? And I will also share some thoughts on how we're changing the spaces that we optimize as a field. What's interesting is that this question matters because it's informed the way that our field has been shaped. So Michael Jordan, the computer scientist, said, "I can't think without metal in my hands." And we see swag for GPU poor. We also see companies essentially assume that scaling is inevitable and state that they're going to do it responsibly. And so the implicit is that this is something which is a given, that we're going to scale and that we're going to build bigger and bigger models. It's also informed how we treat our field, like who's allowed to own what hardware, who's allowed to participate. It has meant that contributions have shifted from academia to industry. It's meant that the way that we publish has changed. It's also determined who gets to participate and who doesn't. So who gets to build the breakthroughs and who is not part of the room when it happens. And so I would say, in many ways, this is one of the most profound questions. It's impacted policy. So even the EU AI Act executive order have this notion that there's a certain inflection point at which models have much more risk. So at 10 to the 26 flops, that's when a model is deemed risky and worthy of further consideration. And what's interesting about this is that it all rests on the presumption that bigger is always better, and that bigger, more capable models imply more risk. And so today, let's ask that together, and let's think about it. So it's worthwhile starting with the role of scale and data in recent breakthroughs. So our recent period of our field and how we've built these breakthroughs seems to tell a very compelling story that bigger is better. So we see that with every new generation model, we've pushed out this size factor. This is across modalities. So vision, NLP tasks, we see ever bigger data sets. It's also involved large increases in both simultaneously. And so we see this massive kind of expansion in both training times, amount of compute, and also the number of parameters of the models. This is captured by Rich Sutton as the bitter lesson. The only thing that matters in the long run is the leveraging of compute. What Rich is saying in the blow to every ego out there is that all our fancy, more complex approaches are not as good as simply leveraging scale. So the first question is Sutton right? Who wants to weigh in? Where's the microphone?
I forgot the question. Can you repeat that?
Is Sutton right?
No, what he said.
He said, okay. Well, let's see, but let's also let people weigh in, and you can kind of gather as we go. Rich Sutton said, all you need is scale. So we don't bother with fancy algorithmic approaches. Just have a general representation. Letting a model learn patterns for itself coupled with scaling. Yes, excellent. Okay, shout it out, and I can repeat.
So we try to do discriminative tasks, right? And we operate on the assumption that reality is discrete, like there are things that exist.
Okay.
Actually, like the data of reality is continuous. So the way that you slice a problem makes it easier to solve or harder to solve, regardless.
Yeah, this is a very nice insight. Part of what you're talking about is our search space, right? So like there may be certain things that we know a lot about, and we sliced it and diced it and created features for and have a lot of domain expertise. You may even be able to get away with maybe statistics there if it's well represented enough, if it's well defined enough, and we have enough previous historical behavior of how it behaves. Nice. So I think that's that point saying Rich is not right, correct? Okay, I gathered. Okay, what else? Who wants to take the point that he is right? Oh, courage, come on. There's many people who think that he just won a Turing. Okay, who thinks he's right? Let's at least do a hypothesis. Why could he be right? Okay, go ahead. Excellent.
Well, I guess you could like if you could train the machine enough, you could argue that they can generalize to learn everything if you give enough.
Yes, this is a very nice point, right? Like, let's say that we have, normally in machine learning, we assume we have access to a sample of the underlying distribution. But if you have all the data in the world and it's well represented, then yes, the model could learn if you train long enough, if you have enough scale. So that's fair. That's like interesting. Yeah. Okay, what else? Why else could he be right? Excellent. Yes. You can shout it out as well.
I think Saturn is partially right.
Okay, excellent.
Maybe he's telling compute as a consequence of having a lot of data. But we care more about information than data. And one evidence of this is that we have to filter a lot of redundant data before training a data set. So maybe he's partially right because we need a lot of compute if we have a lot of data, but maybe if we find a way to actually have more meaningful information, we will have more efficient models in the end.
This is excellent. So this is a point which we'll talk about later, which is that this notion of scaling and more compute, by delegating representation to the model, we're saying we don't actually want to specify how features are extracted or what's extracted. And what I think Omar is suggesting is that because of that, we scale way more the compute because we may be throwing in junk. So we can get to that later. Yeah, that's interesting. Maybe one more point here. Who would like to speak? Excellent. Yes. Yeah.
Improvement. Thanks.
It's okay, I can repeat if you continue.
Right, I think Sudon's partially right. Right in the sense that scale usually brings improvements in models, not right in the sense that we shouldn't bother with algorithmic improvements. I think those two axes are somewhat orthogonal, so given any amount of compute with better algorithms, we can achieve better performance, and also the other way around. Given some algorithms, we could scale them up and achieve better performance.
Yeah, very sensible answer. I love this one. It was very, yes, okay, nice. I think what you're saying is for a given amount of compute, we can use it in from ways which range from poor to excellent, right? So given a fixed amount of compute, how we use it is interesting. But more compute, we could always fill the space of like available use cases, even if we make it more efficient. Very fun. Okay, let's go for it. So there is an argument in favor of this approach, and I'm surprised no one said it. Evidence. There is really all the breakthroughs over the last decade or so have been us throwing compute at the problem. So this is a very compelling reason we should pay attention to this. And it's a very simple formula, which also, I think, appeals in some ways. But we see this in many ways. We see that size often kind of confers different properties. We can disagree about what they're called. There's an active debate if they're really emergent or surprising. But there's no denying that we see large differences between scales. So like even quantization sensitivity changes a lot above 7 billion parameters than it is below. And so we see a better propensity to model and more fluid responses for generative models. We also just see simple differences, like for instruction tuning, this idea of few-shot performance really depends on scale. So you can have good zero-shot performance, however we define that. It's kind of also an active debate whether anything is truly unseen. But we can have better interpolation properties if we're above a certain scale. So this again suggests that scale is important. If you look at chatbot arena, so the best models, so it's quite interesting because the model which reveals its parameter size that's the best is DeepSeek, but even that is very hefty, so 685 billion parameters. So this is very large models that are dominating the top of our leaderboards. And what's interesting is that a key limitation of this approach of just throwing compute into, and by the way, one of the reasons I would argue this is very favored is that unfortunately, even in industry labs where a lot of the computers, you have quarterly bets. And it's very easy to say, let's throw more compute at it. It's much harder to say, let's revisit some of the core building blocks of our algorithms. This is interesting because it still doesn't address one of the core limitations of this approach, which is that we don't actually know that much about the relationship between parameters and generalization. And there's a few data points I'll share here. So models at the same performance are getting, at same parameter size, are getting better over time. But also, small models frequently outperform larger models. So all models over 13 billion are in the gray. And then the best daily model is in green. So this is the open leaderboard on Hugging Face. And it shows that we see more and more large models over time being outperformed by the best small models. We also see this with our work. So iExpanse outperforms far larger models. We even amplified this with IA Vision. So we outperformed models 11 times its size. So our model outperforms Llama, which is 90 billion. And what's interesting about this is that this is part of a larger picture where we have actually a very highly uncertain relationship between compute and performance. Why? And maybe I'll share some data points. So one is what was brought up actually during our discussion. So this idea that data quality compensates for the need for compute. So we find that repeatedly, if you remove low quality data, you can arrive at the same level of performance using less data. So things like deduplication, pruning, more highly optimized estimation of quality. We released work, I think a year or so ago, led by Max Marion. So this shows we extended to pre-training at scale. And we use very simple estimators to remove the majority of data. And what we find is that you can achieve the same performance while training at as little as 30%. And this is at pre-training scale. And we also show this for even annotation. So if we prioritize where we apply human annotation, we can achieve the same performance and avoid ties much more effectively. But we also see this in the fact that the relationship between weights itself is not well understood. So diminishing returns to adding parameters. So this is an old school example. So we saw this in computer vision, which convolutional neural networks saturated on many of the tasks that we use to measure progress. This is inception v3 versus v4. So you double the number of parameters from 21 million to 41 million, but you only see 2 percentage points in accuracy. And this is an example for convolutional neural networks, but arguably, we see the same now. So recent releases are often 11 times the estimated parameter count of previous ones, but there's a noticeable shift in the expectation of what gains can be achieved with transformer-style architectures. There's also redundancies between weights. So researchers, this is a very nice paper. Nando's on this, nice. I knew it was one of it was one of the early papers from Misha. They find that you can predict the values of the weights in the network using a tiny holdout, so just 5%. And furthermore, like if we need so many weights, why can we get rid of them all afterwards? So we did this very nice landscape survey on sparsity. A lot of my earlier work was on sparsity, and you can achieve incredibly high levels of sparsity without giving up performance. What's interesting about this is that what it suggests is all these weights are mainly needed to condition your optimization space during training. And afterwards, we can get rid of it. So in some ways, this is telling us we're bad at optimizing. And once you realize that, you start to think, wow, we're really inefficient in how we train these networks. And a lot of this is because we've chosen empirical risk minimization. So we optimize for average error. What this means is it takes more capacity and longer training to learn. And the majority of features are learned early in training, but we spend massive amounts of the training period learning these rare features. I did a lot of work on understanding the role of capacity. So what do we learn as we vary the size of these networks? And what we find is that actually the majority of weights are used for a tiny slice of the distribution. So when you remove 90% of weights, what you lose is the rare examples in the data set. Put differently, we're using the majority of weights to encode a useful representation for a tiny slice of the overall distribution you care about. I have some examples here. Who wants to guess what this example is? Disk. This is a toilet seat. And here I have another example. So this is scale independent. It's not impacted the performance as you vary the size of the network, but this is scale dependent. What about this? Beer. This is espresso. And then this is maize. What about this? Women, perfume. Plastic bag, nice. Who said bag? Excellent, yeah. What about this? Star Wars, okay, actually very worthy guess. Yep, cloak. So you may have gathered these are very difficult examples, and this is what you lose as you vary capacity. We did other work which shows the learning trajectories, and most typical examples are learned extremely quickly at the very beginning of training. In fact, most of our pre-training compute, these massive amounts of compute, are learning the long tail of examples. And we see there's two types that we rarely distinguish in machine learning because we don't treat source of uncertainty. So we have both atypical and noisy examples, which have very different sources of uncertainty. So one is reducible. If we have enough examples of something atypical, we'll learn it. Another is noisy. It's irreducible. We just have to remove it. But right now, all our ways of addressing this really struggle to differentiate. And so some of this early work was trying to leverage patterns and loss trajectory to try and identify different signatures for these different examples. The other thing that is interesting and which really causes chaos with our ability to understand the relationship between compute and performance is the role of architecture. Why would architecture matter? Who wants to jump in? Okay, Enzo, go for it. Nice.
Because of syntactic bias, some of them are pretty good for different type of data.
Excellent. Inductive bias. What do we mean by that? Like, what's an inductive bias of like some of our popular architectures? Okay, excellent. Said like he's taught a computer vision course. Excellent. Nice. I don't know if you're allowed to answer. Bravo. Yeah, what else? So I think what we had there was some of the properties of convolutional neural networks. Nice. What else? Okay, excellent. Yes, this is another one. So these are really nice because they allow extraction of features more efficiently. So convolutional neural networks really reduce the computational costs because of this. Yeah. What else? Oh, excellent. Two hands, side by side. Let's go. Okay, you go first.
Frequency bias.
Oh, tell me more. What do you mean by frequency bias?
Well, especially in vision, lower frequencies are earlier during training.
Bravo. Okay, I do love that. Very timely. Nice tying in. Yes, I mean, because of our objective functions. You know, it's interesting, though, because that's a property of deep neural networks and our loss functions. Yeah, it's very interesting. And I think we haven't merged beyond that when we've gone from convolutional networks to transformers. They're both characterized by this. We're still doing... Oh, okay. Oh, okay. Wow. That was very different. Okay, excellent. I'll go with this one. So yeah, I think that's a very nice example that's characterizing all our deep neural networks. And in general, any optimizer that is leveraging a kind of batch aggregate loss function. Nice. And then to your, yeah. Yes, so you're getting to the heart of the question of why this matters. So why architecture has been one of the most fundamental shifts in our scaling properties. That's why no scaling law could have been predicted before convolutional networks, and no convolutional neural networks scaling law could be applied to transformers. They fundamentally change the search space because often they're changing the properties of scaling and changing the efficiency of doing so. Yeah, anyone else want to add to this prior's conversation? I think it's very important because I actually think we forget how heavy our priors are. Like something like tokenization, extremely heavy prior, right? We're representing all of our input space in a way that's already quite dense. So we've made a decision about how to represent it. Language itself is a heavy prior, right? It's dictated by our communication rate. So most languages have the same rate of communication. And I think that's often forgotten, is that the way our data is represented is really a prior of our physics and our limitations in ability to process different inputs. For example, all audio data that is recorded to be deemed worthy of recording, it's mostly in the frequency that we can hear. And it's very interesting because even cameras process images automatically before we even process them to make it look like how we see the world. So priors, we talk about it in architecture, but it's very heavy in the data space as well. This is a very worthy conversation to have. Okay, any more ideas here? What are the priors? Okay, go on.
The difference between VITs and swing transformers, swing windows to capture the hierarchy.
Yep, this is very true. So sliding window attention, this is very interesting, and this is getting at, different context lens. It's really unlocked a lot of our ability to do that. Okay, so this is important. I think that so much of what's interesting to think about is that we really adopted neural networks based on empirical success, but there was a long body of work which led to that. And we've already talked about some of these aspects, but one of the critical reasons why this was able to process a high-dimensional input space. So images were traditionally thought of as so high-dimensional that most of the work in the 2000s was about feature reduction. So handcrafted features like Sobel edge filters that would try and reduce the dimensionality before you even process it. And the reason why convolutional neural networks were effective is that they made it more efficient to extract features. Shared weight, so we've talked a little bit about this, but the shared weight kernels mean that you can apply the same filters across an image, which makes it very efficient. Pooling operations, so this is notoriously something that Jeffrey Hinton is very cross about, and he always says it's really unfortunate that it works so well, and so it stuck around, because if you think about what a max pooling operation is you basically only take the maximum value and you discard everything else. So it's incredibly hacky, and it's shocking that it works, but it allows us to dramatically reduce information and makes it way more efficient. And then also hierarchical feature extraction, which we've gone in a few places, but each subsequent layer kind of builds. So you see different features emerge. And so, for example, early layers of the network are known for really being edge extractors. I think this is much more clear in convolutional neural networks even. And then we see transformers. So we see self-attention mechanism, the parallelizable nature. So it scales much better. And that's one of the reasons, even for vision problems, a lot of people have switched to transformer because of the scalability, which is interesting. It's actually not clear. I think there's very fun work to be done there in the future. And then the lack of recursion. So because of this ability to extend context, you gain a lot. And so I would argue that it's both algorithmic and also architecture innovation that determine the rate of return for compute. And this is what the very nuanced comment at the beginning was getting at, is that it's this rate of return that matters. So for a finite amount of compute, you want to understand how much do I get back in performance. And this means that compute alone does not dictate the pace of progress in our field. And what's often missed in this statement is that architectures to date have very much dictated both that slope as well as the ceiling. And it's very interesting to think about that because it's the most important prior in conditioning the search space available. And so this will lead nicely into what we'll talk about next, which is what now? So where do we end up? So I may have convinced you that we are now in a period of decreasing returns in compute, but maybe I don't have to. I think all I have to convince you of today is that it's very expensive to follow our current optimization protocol. So even if we're not in decreasing returns, the amount that we pay for increased performance is very high. We're paying a lot to learn rare and atypical features. And as a point of comparison, our brain is incredibly efficient. So we run on the energy equivalent of an electric shaver, and that's because of key choices that embed efficiency. So there's pathways which allow us to combine certain inputs with higher efficiency. For example, it's much easier for you to walk and talk than walk and read. We also are very good at certain tasks and very bad for others. Like, we're very bad at sequential processing. As much as we love chain of thought, we like it because that's how we have to think through difficult problems, not because it's inherently the way that these models should think through difficult problems. I think my hot take is I think chain of thought is a temporary Band-Aid because it's really just trying to mimic something where these models are already very good at parallelizing a lot of these challenging questions that we have to do sequentially. And then we simulate a lot of what we see. So unless I move, like now, if I stay still, you're probably simulating it. You're not doing a full forward-backward pass, which is very energy efficient. And we have log-scale vision, so you won't notice unless I do something sizable. And there's a reason for that, because we don't want to absorb all the information around us. We want to prioritize. We also, and I think this is often very much underestimated as a factor of our intelligence, are able to perturb our environment. We have movement. So if I am not sure about something, I can walk forward, I can pick up, and this gives us a very good calibration of uncertainty. And we use this all together, which for most of computer science history we haven't, so it's very interesting. And then, in contrast, a lot of what we do with deep neural networks is painfully inefficient. So we don't have adaptive compute. We have a mixture of experts, but they're not exactly specialized. They're more like a hack for our inference budget. We increasingly also have these really tricky things where we're still seeing all examples at least once. And we use global updates. So that means that we have things like catastrophic forgetting. We forget what we previously learned in these networks. We also really have these batch issues where we're optimizing for batch performance. So where do we end up? I think here. This is the next part of the talk. If scaling is slowly dying, where do we go next? Or how do we change this rate of return for compute? I do love this quote. So what we have before us is some breathtaking opportunities disguised as insoluble problems. Oh, it's okay, I'll hold. People can take photos. I do like this quote. I think what's important to remember is that computer science as a field is very young. So it's only been around 77 years. And our pursuit as a field has really focused around this idea of optimizing an algorithm. We abstract away, in the research field, we abstract away typically the data set, and we abstract away typically the deployment, and we focus on the model. And the pursuit has always been this general, intelligent machine. And what's fascinating about that is that I would argue that within the last 2 years has fundamentally changed in a very significant way. And our tools for optimizing as a field are profoundly changing very rapidly. And that the focus is not just the algorithm. I will say that we now optimize in the data space, which has been something that wasn't possible before. But also, we are experimenting more and more with gradient-free performance boosts, meaning we don't update the weights at all. We just do acrobatics around the weights and see performance gains. This fundamentally changes how we teach computer science, how we think about our optimization tools, and our purview of responsibility as researchers. And this is fun, I would say. So what do I mean? I'll talk about all of these, but I'll start here. We have some promising directions for optimizing in the data space. One is pruning, which I talked about earlier. I would argue that this is really articulated as spending more capacity on the data we care about, trying to isolate those noisy data points and remove them. trying to, if you're able to, remove some of the more frequent and focus on the less frequent. And we've done a lot of work on that. I won't spend too much time here. But I think that that's really about addressing the misuse of capacity. We don't want to spend time on noisy data because it's not learnable, even if we throw compute at it. So it's largely a regularization problem. I would argue this is largely the issue of our pre-training. Our pre-trained models have to be massive because we're throwing the garbage of the internet at it. And if we were able to have a successful estimator to identify what was better quality, or if we were able to scale the data that we have that's higher quality later on, we wouldn't have to divide it into this hacky three-stage process: pre-training, instruction fine-tuning, and then preference training. Because one of the key things that's varying there is just the structure of the data. And we just are trying to steer it to be more like the distribution we want to serve, and less like the distribution we have readily available. And so we've done a lot of work on pruning. I'll put this here. But here's where I want to spend time today, which is this idea of moving away from static data sets, so optimizing in the data space. I would suggest that this is very specific to this point in time. So we've largely treated data sets as fixed. Why? Why do we treat them as fixed previously? Is that a hand? No. Oh, it went down so quickly. That was excellent reflexes. Who wants to speak here? Yeah, excellent. Go ahead. Okay. One at a time. Yeah, go for it. Whoever was first.
Expensive to collect.
Yes, it's so expensive to collect. Yes. Who else? Well, who's going to say something next? Excellent.
Benchmarks like ImageNet, make training on ImageNet, evaluating on ImageNet.
Okay, so in what sense? Like they're expensive to collect, they're...
It's available and everyone are comparing.
Okay. This is a fun point. What you're saying is you get stuck as a research field. Yeah, why would you collect another data set when people will want you to benchmark on ImageNet anyways? Okay, bravo. This is a very nice point. This is a point I call the stickiness of science. It's why we were stuck with adversarial LP norm research for too long. Slightly cheeky side comment there. Okay, what else? Yeah, very nice. Go ahead.
Okay, so I previously worked on lower source languages.
Yes.
So in that case, sometimes, and I will say most of the times, native speakers do not agree on some things that the rest of people think they agree.
Yes.
Like
yes.
Dialects or
Yep.
definitions, alphabets, etc.
Yeah, this is actually very important as a concept, inner annotator variability. So any given concept, whether it's a single classification, discrete space, or if it's a notion of how to take on a task, annotator variability is very high. And the notion of ground truth as we know as a single label is actually a myth in the real world often. So this is a very nice point. So you have to reconcile. So not only do you have to collect, you have to reconcile. What else? Maybe one more comment here. Who wants to go? Okay, I have two, so we'll do two. Nice, go ahead.
It's difficult to convince people to evaluate their models on new data sets.
Yes. Okay, so that was a nice +1. This is good. I agree. I think there's an inherent inertia in absorbing new benchmarks. We're seeing that now with language, is that benchmarks are so quickly saturating. It's making it very, people are not sure where to jump to, what will last. Yeah, okay, and then we had one more. There was someone, okay, maybe over there. Yeah, go ahead.
I was thinking it's difficult to know when you change the data set if you have improved because you have
Yes.
Yeah,
Yeah, the lack of reference point. Yeah, very nice. And part of what you're all getting at is it's a lot of effort to create a new benchmark, right? So yeah, all this work, so the cost of annotation, annotator variability, we haven't talked about this, but there's also just difficulties obtaining some types of data, right? So there's a selection bias in who will respond or provide data. And often you end up with weird biases in what parts of the distribution that captures. But what it means was, until very recently, we were stuck with the data that was collected. and with the issues of the original net annotation. So I actually did do a grumpy paper about ImageNet. This was what do compressed deep neural networks forget. We found that a lot of what was most sensitive to capacity was the incorrect examples. And so when you scale, you just memorize the incorrect. So it's very interesting. I think that this is what makes it so profound, I would argue, and there's two reasons for that. One is that it makes the label space a lot cheaper. So I've been involved with the data provenance initiative. We've done a lot of work characterizing the data we have available and the data provenance. A lot of what we've relied on, because we've worked with thousands of data sets, is a combination of expert annotation and also using LLMs to provide proxies to understand the scale. But this is important because often our desires for annotation change across time. So our data sets and how they're used are not fixed, but are often revisited. I wouldn't use synthetic data yet, but I think about something like harm. I do a lot of work on fairness. And fairness is very tricky because the notion of fairness changes over time and across time. So by geography, we have different power dynamics. So in the US, there's legally protected features like race and gender, but in India, it's caste, and in Africa, it's often tribe. And what's interesting is that it's also, you can think of this as even how over time our language uses change. So if you think about your favorite comedy show or comedian from 10 years ago, if you rewatch them now, it might be a bit awkward. You know, like our humor and our boundaries changes over time. And so this is why we want ways to revisit data and are more nimble and to catch things that we didn't catch before. But the second, and I think this is very important, is that synthetic data being good enough allows us to think differently about our primary construct in machine learning classes, which is sampling IIDs. So you sample, and it's representative of your distribution, your underlying raw distribution. And why this hasn't worked for things like NLP or for other problems is that your sample often is completely different from how you want the model to generate in the end. And so you're doing all these acrobatics after you sample to try and get it closer to what you want. And what synthetic data does, it allows us to think about strategically structuring our distribution, which is very profound. When you sample at random, you end up with all those inefficiencies we talked about. But if you target your synthetic data creation, you can start to think about the parts of the distribution that you most need to improve in. So self-driving cars is a very intuitive example of this. This is a poor Waymo that got stuck in cement. I actually love Waymo, but this one was not so lucky. But those are the type of examples that actually we want more of, because they're very rare, but when they happen, they can be very, it takes the car out of commission. There's also examples of different weather conditions. And if you can simulate more data in those parts of the distribution, you can see a lot of very important gains in performance. The criteria being you need a teacher that's performant enough. So this is Louisa. I think Louisa's somewhere here. Okay, Louisa's there, nice. So this is work that we did that I think is very nice, which gets at this, which is, okay, so we know now that it's feasible and cheap enough to shape the data space. How much can we shape it? Can we steer it? And so what we did was we looked at really thinking about how do we kind of condition teachers towards certain properties of the data. We call this active inheritance. And we aim for non-differentiable properties, which is also fun to think about, because so much of our optimization depends upon it being differentiable. And what we show is we can see massive gains in properties that we target. So we looked at text diversity, which means the richness of the text, so improving text richness and toxicity as well as length. And we look at passively versus actively inheriting. And what this is part of a wider body of work. This was led by Yamade, where we strategically sample from a pool of teachers to craft the distribution that we want. And we target teachers which are good at certain parts of the distribution. And this is where I think we also start to avoid mode collapse. So properties where we oversample from a given teacher, so we just inherit passively all the limitations of that teacher. I'm going to, how much time do I have? Excellent. Okay, we're good. Nice. So let's talk about this gradient-free performance boost. So what is a gradient-free performance boost? Let's go. It's a bingo card. There are a few, so let's go. Who has one? Excellent. Yes, go for it. Pardon? Chain of thought. Yes, that's on the list. Yeah, technically, yeah, very nice. It's very, yeah, perfect. Yeah, go ahead. Okay. Technically, that's not gradient-free because you still need to train the model. But I have looped in some things there, like, so data distillation, so synthetic data distillation, technically you do still train, but you're sampling the entire data space and it reduces your number of gradient updates that you need. So I think that could fit into that, like low compute. Yeah. Go ahead. Excellent. Yes. Yeah. Yeah. Bravo. So you're talking about applying rule-based approaches on top of models. Yeah. Yeah. So I actually think this is a very profound point because it gets to this idea that sometimes the cheapest way to address something is to apply a much simpler approach on top of a model, whether that be in the pre-processing step or if it be like how the model is presented. We see this actually with a lot of our current models. The way that they're actually hosted often involves rules applied on top of the model, very simple rules, and it's kind of fascinating to see. Like, for example, on certain onboarding flows, you'll just ask what your name is, and then that is applied as like a conditioning of the preamble. So it's not a rule, but it's a very cheap trick. No gradient updates required, but it achieves the same effect of like a big boost and like you're feeling that it's addressed at you. It's very interesting. Another rule that actually is very interesting for performance is speculative, like this idea of decoding immediately as you have tokens. So the streaming of tokens. This actually makes no difference to the optimization, but it makes a difference to how we receive the algorithm. We like to see it appear as it processes, otherwise it feels like high latency. So this is very fun. I like this point. What else?
In the case of LLMs, prompting techniques like few-shot prompting.
Oh, nice. Yes, very good. Yeah, so few-shot prompting, excellent. That's on the bingo card. Yeah. Okay, nice. We have a triangle. Go for it, João. Majority voting, very nice. Yeah, actually we see that a lot in both LLM as a judge, reward models, as well as you can imagine some of these best of K sampling methods could also be framed as majority voting methods, so very nice. Yep, okay, who is next? Yeah, go ahead.
I would say that what I would call best of K sampling or self-consistency.
Yes. Yeah, all these fall into the same nice bucket of approaches. Self-consistency is nice. What is self-consistency for people who don't know it?
It's sampling different solutions for the same problem and picking the majority of the solutions. Like different solutions for different results and the most common result.
Yeah, very nice. So I guess the difference is for self-consistency, often you don't need a reward model. For best of K, you sample multiple times and then you use some external score. For self-consistency, often you just measure the similarity or like you can measure some other indication and then you can go from there. So it's very nice. These are all, the cost is an inference pass, but you're not updating any parameters. Yeah, and then we had some, oh nice, okay. RAG, yes. Beam search, yes. This is very interesting. I like both these. Okay. Yeah, go ahead. Pardon? What's reflection? Yes, yeah, reflection or reasoning. Yeah. This is very nice. Yeah, you can have multiple stages where the partial or critique, so another version of this. Very nice. Maybe one more here and then we'll go. RAG, this also counts. I think RAG is very nice. It's one of the examples I have as well. Yeah, so we're just seeing this yeah, I think here the question is, what can we do when we don't allow for any gradient updates? And it turns out a lot. And part of why I think this has been unlocked recently is that when we have generative models, it actually creates a very rich interpolation space. And there's many ways we can traverse that. And prompting has always been a very hacky way of traversing that. That's why your prompts don't work when you go from one model generation to another, because it's almost like we're tea leaf reading. We're like, what works for this particular high dimensional space? But I see increasingly that we're getting more sophisticated approaches of conditioning the space and extracting the best performance. And this is super interesting. So we have things that require some compute. So some of the most profound developments have been things like multitask, instruction preference, chain of thought. Arguably, you can either use in training or you can use it inference, reasoning. And oftentimes you need some examples to show the model to induce good behavior like this, but it's very limited. And sometimes you can just do a zero shot. So it can also be like a zero compute technique. But as was mentioned, there's even more that don't require. And I'm surprised no one said maybe one of the most, I guess, popular directions right now, but it includes things like tool use, RAG is an important one, best event sampling, self-consistency, a lot of ones which are about majority vote. I like that that was brought up. Distillation is an interesting one. I also put it here because you could use distillation and then put it in FuseShot, but it kind of belongs in between. It reduces compute costs, but if you use it for training, it's not compute free. Increasing context length. This is another profound one, right? So even RAG and introducing context length, these are different ways, and they have different properties, but they're different ways of extending your database beyond parametric, beyond weights. And then model merging and agents. I'll just point out, so we did a lot of work on model merging. This can be very effective for balancing multiple objectives. This is work led by Akansha. And this is very good when you actually have very distinct models and you need to merge the properties. And it requires zero gradient updates. So you're just merging at inference time and you can on the fly come up with a different balance of properties. There are very interesting questions about when is the weight space too different to do something like this, and what is the best conditioning of the weight space to make it a good merge, which I think is fun to think about. And then we've also done work on RAG, so this is led by another Louisa with a Z, but this is work that we use RAG to do continual learning. So I'm going to stop here and open up. I do want to leave one big picture idea, which is that I would argue most of our intelligence is gradient free. So what that means is that, you know, we develop as humans. We definitely, our brain develops and changes. But our intelligence as humans is not individual. I hate to crush the ego of everyone out there. But most of our intelligence comes from the ability that we are in this room sitting like this, that I'm standing, that everyone knew to arrive here at a certain time, that everyone had a notion of the nature of this discourse that we're having. And that's mainly based on our desire to belong and to really adhere to like our societal norms. It's a very collective intelligence in that sense because it makes global updates very cheap. I think that this is something that is often missed in how we framed our pursuit of intelligence, is that the notion of mimicking the human brain is actually not really the goal. But it's our collective knowledge that is the objective. And our desire to combine that knowledge, which is very inherent to how we are incentivized. And the reason why I bring that up is that I think that it's very interesting as we move into this new era of this expanded optimization space to think about these notions of units like models combine and optimize in different ways. I'll be candid, the biggest game changer is still going to come from a change to that unit. The next architecture is still very critical because it changes the rate of return of everything else. But this is a very exciting time to be working on these topics because our levers are much more varied. So I think it's very possible, and I would argue necessary, that the next breakthrough will fundamentally require a different way of modeling the world, and may require a different combination of hardware, software, and algorithm. I didn't talk about the hardware lottery here, but I think we're very much in it. NVIDIA is calling its, its recent line of GPUs, it's the transformer engine. So we've just doubled down and put all our poker chips on the table for deep neural networks. So hardware and software matter too. But I think that compute is the least interesting thing to throw at a problem. And increasingly, we should be asking ourselves to justify additional complexity. So I think here we can learn from hardware architects. So Moore's Law is a very nice example. So Moore's Law was released in 1965, and it was this idea that by shrinking transistors, you could double the amount of transistors on a chip. It turned into a self-fulfilling prophecy, but unfortunately, it made the life of a hardware architect extremely boring. Very risk adverse, because the whole goal was you could still get a lot of gains from transistors, and so the whole field became about pushing transistors onto a chip. One of my favorite Turing lectures is by David Patterson and John Hennessy, and the end of Moore's Law is slowly approaching. Moore's Law is something else that's slowly dying. And David said, actually, this is very good for the field of computer architecture, because life is not boring anymore. And in fact, it's the golden era for designing architecture, because there's much to do. And so I think this is a lesson we should take to heart, because this field is going to change very fundamentally and probably for the better. And with that, thank you so much. This is amazing. Thank you. So I don't know if we have time for, do we have time for questions? One, two, okay. Okay, here we go. Yeah, so I'll take the hand over there. Yeah, I can repeat it out. Oh, okay, there we go. Yeah, I can repeat it, yeah. Yeah. Also becomes harder. So you start thinking about it, and it's like you have to take 15, 20 years of like advances in the field back and just go to the essentials again. So I think it's very scary for a lot of researchers to try and just diverge so significantly from the current paradigm of developing the computer. Yeah. So I probably won't repeat that into the microphone. But I do think you're pointing out a very good grumpy point, which is that it's very hard to stray from the beaten path. I kind of got at this at the very end, But another good example is capsule networks. So capsule networks were Geoffrey Hinton's the ideas that him and Sarah Sabor worked on, and I thought it was a fun idea because it was trying to do something different from convolutional neural networks. At least it was trying to say, well, there's some things about convolutional neural networks that are not great. That, you know, an image is still processed even though it's all still scrambled because we apply the same filters everywhere and it's still classified as an image. Another thing like this is state space models, right? So it's also doing something interesting that's different. And the sticking point is hardware, and it's because we've optimized, and frankly, I'll say more about software as well. So with capsule networks, squashing operations were a massive issue. There's a very excellent paper called Machine Learning Systems Are Stuck in a Rut. And the researchers who helped Geoffrey Hinton implement his system, because Geoffrey Hinton famously works in MATLAB, wrote this paper after having to implement capsule networks. But it was all about how our systems are broken. We've over-indexed. And the reason why is efficiency. By domain-specialized hardware, we've really indexed on one operation only. What is that? Who wants to throw it out? What have we optimized for with all our GPUs? Bravo, nice, yeah. So matrix multiplies. But I will say it's also this, it's software. And what I mean by that is that it's also very difficult to port any part of your stack right now. Like if I work on TPUs, I'm working on JAX. If I'm working on GPUs, I'm probably working on PyTorch. The portability is extremely limited, so if you go from GPUs to TPUs, you're losing automatically 40% of PyTorch functions. And then you get a slowdown for the rest. And so you're locked into your stack, which means you cannot experiment or see different patterns in your ideas. And this is equally dangerous. So it's a software portability issue too. So I don't have a response, but I do heartily +1. And I think that's a very critical problem. We are probably out of time. Yeah, excellent. Thank you, everyone. That was so nice.